Okay, good afternoon, good morning, good evening, everybody. Thank you again to join our already traditional CASS talks and Professor Cláudio Diniz from Catholic University of Pelotas will be the session chair today.
Okay, thank you, Professor Reis. Thanks for the opportunity to introduce Professor Sergio Bampi. So Professor Sergio Bampi is a bachelor in electronics and physics from the Federal University of Rio Grande do Sul. And he has also a master and PhD degrees in electrical engineering from Stanford University. He joined the Federal University of Rio Grande do Sul Microelectronics Group at Informatics Institute in '86, where he is currently a full professor. He serves now as a PhD advisor and principal investigator in microelectronics and computer science programs at UFRGS since 1988. He worked as a technical director of the Microelectronics Center, CETEC, from 2005 to 2008. He was also a visiting research professor at Stanford University and director of the National Supercomputer Center at his university. His research interests are in the area of IC design and modeling, mixed signal CMOS circuit design. Architectures and SoCs for image and video processing, nano-CMOS device and ultra-low power CMOS design, and also dedicated complex algorithms architecture. He has more than 420 papers in the fields of mod devices, circuits, technology, and CAD. He was also the coordinator of the graduate program in microelectronics at his university. He is now a IEEE senior member and is member of CASS, SSCS, EDS, and CIDA. So thanks, Professor Sergio Bampi, to accepting our invitation, and the floor is yours for the presentation of our talk.
Okay, thank you all for being here and listening. Thanks for the IEEE Circuits and Systems Society chapter of Rio Grande do Sul for holding this series and inviting me. I'll be talking about near threshold logic and some mixed modes circuits design. Targeting for maximum CMOS energy efficiency, and the market for that and the application is IoT devices. I'm Sergio Bampi. I work at the Federal University at the graduate program Microelectronics and graduate program Computing. Here is the agenda for today. Basically, I'll talk very briefly about the computing challenges and very low energy applications. What is wide voltage frequency scale? How it's possible to apply very wide voltage frequency scaling, and then go into the main part, which is near threshold computing, and then deal with optimized digital cells design for ultra low VDD and also variability, and then at the end we'll talk about some low frequency analog signal amplification results in which are using digital based functions to perform low frequency and low performance analog signal amplification, and then wrap up. So the grand challenges of the IoT era is that you want devices that are always on everywhere. They have to be very, very cheap and pervasive. Everywhere. From current, let's say, assessment of today's situation on IoT, some different market research say that we are on the order of 20 to 30 billion devices, interconnected. Yeah, suppose we jump 50x from today, that will bring us to Orwell scenario where we have like a tera objects connected to the internet and all sending information. But if you evolve, like say 10x in the IoT, the number of interconnected devices in the next 5 years, that would be already a big jump. It would be on the order of 200 billion devices connected. All those predictions are really uncertain, depending on where you listen to, how this market research are done. They come up with different numbers, but that 200 billion objects is within the 10 years frontier. And there's another grand challenge that will basically revolutionize our living, is the electronics in the brain, electronics in living beings. and that would be a new era for, let's say, how people live and the interaction of electronics with the living beings. And all of that will be cyber physical. I don't foresee that we'll be all cyborgs in the very near future, but we are being used in very lots of systems in factories, in controlling devices. That's the IoT. It's a cyber physical, one part of the cyber physical space, and IoT and cyber physical has to be rigorously defined. They're not the same thing. Enabling all of that is the evolution of system on chip, and so there are revolutions going on in computing and coming out of the impact of computing at this level. And one key point is that the heterogeneity of hardware. There will be more heterogeneity for this cyber physical system, for flexible electronics, plastic electronics, and eventually, electronics compatible to working smoothly with human beings and living beings. All of that requires nanowatts power level for many of them to be autonomic. And we are talking about implementation at nanowatt at a giga scale digital integration, and that's enabled by today nano-electronics. And we all know the benefits of chip scaling. The economics of it are a very compelling drive force. So you can have more dies and more functions per unit area in your wafer. So stepping, going forward 3 generations, you can basically multiply by 9 the number of chips on a wafer. That's really an economic driver. Now we're going to go to the limit of 2D scaling. I'm not going to talk about those issues. I'm going to talk about near threshold computing, which is one key solution to reduce energy consumption. That means voltage scaling. And lowering the supply voltage to near the threshold voltage, that's what near threshold computing means. And the key point here is that near threshold allows, it's been demonstrated experimentally over the last 2 decades, you can gain a factor of 10x in energy efficiency by reducing both dynamic and static energy in a superlinearly fashion. We all know that the supply voltage is adjusted to compute load in many cores, in GPUs, in SoCs with hundreds of top-level blocks. And also, when I say just as definition, NTC refers to near threshold voltage computing. Some say NTV, near threshold voltage, but that's what we are talking about. That has been demonstrated. This is an experiment done more than 10 years ago at Intel in a 65 nanometer circuit. They took a small core here with about 100,000 transistors. It's a motion estimation engine, and then they fabricate it and make some small changes in the memory. But anyway, they scale down the voltage, and then you can see the frequency goes down from gigahertz down to a few megahertz. So you vary by a factor of more than 2 orders of magnitude the frequency. And moreover, the power scales from 100 milliwatts to little above 20, 30 microwatts. So you scale power by more than 3 orders of magnitude, and frequency by little over 2 orders of magnitude. The most important demonstration of this experiment is that if you take the number of operations, in this case, operation is motion estimation and computation. If you take a meaningful, operations that's performed by this VLSI hardware, the number of gigaops per watt, increases as you go down in performance. Performance means going down in frequency. And when you enter here in the near threshold, you're near the threshold. The VDD is around your threshold. There is an exponential decrease of the frequency. But if you are allowed to operate in near threshold, the number of gigaops per operation, which is basically, gigawatts per watt, which basically is the inverse, of the number of joules per operation. So they have the joules per operation has a minimum around here, and the number of ops, per watt, ops per second per watt, peaks at around, in this case, 320 millivolts. They were functional down to 240 millivolts because of the memory and the way they did registers. Okay, but you know that most of the companies, prefer to do scaling. If you have, let's say, a 2.5 volt nominal, they scale, in older technology, they scale, very mildly here. And it's very well known in CMOS that the delay can mature technology can go by a factor of 2 or 3 if you go from 2.5 to 1 volt. So it's well known that performance deteriorates, CMOS performance. So voltage frequency scaling is a very widely adopted techniques, and dynamic voltage frequency scaling indeed provides a runtime capability for doing finding the power mode operation that really saves more energy. So that's based on exploring the workload variation. That's done everything from high-end server processor all the way to very light energy devices. Now, if you look at the high end, the industry applies, let's say, a narrow range. For their standards, not narrow, but from what I'm considering here, a narrow range of operating frequency from, let's say, 2 to 10x. So different operating modes allow, let's say, by stepping the VDD using voltage regulators, it's better that the voltage regulators are on chip in your SoC. So using voltage regulation techniques, they can step down blocks, by 10, they supply by 10 or 15 millivolts steps. But they do arrangement in different power modes for those devices in a range that's very limited from nominal down to, let's say, 200 millivolts below nominal. So the main reason is that they do have a very narrow dynamic voltage frequency scale is because they don't want to fall off in this exponential, let's say, fall off regime in which you don't have any more performance below half a volt. And this is what I was talking about. I have several modules here, different modules that you have here. They will have sensors, for thermal, sensors for monitoring the agent, most likely some ring oscillator, current sensors, and some modules, voltage sensors, and then the maximum frequency is really adapted. Okay, so you adapt VDD, and then you change the regulator voltage, and then you adapt the frequency in this model. So every core, every processor here can operate in a different voltage and frequency settings, set control. And those are the power configuration modes that's very much standard of the industry today, as you know. That's what I mean. So they have, in practice, in commercial products, you have to limit the maximum voltage, and now you have voltage increasing in this scale here, right? And so voltage is increasing here, and the minimum voltage that you can set is set up by basically how low performance can you tolerate in your application, and the maximum is delimited by the reliability, and let's say basically aging and reliability effects and system failure that comes over time, especially if you have temperatures that rise. So all of that, comes into what is the minimum limiter things. It's basically circuit functional failures, because you're giving frequency, or you have more prone to soft errors, and so you avoid this region here in most commercial products for computing, normal computing. But also, if you bring down the voltage, you can have benefits in terms of aging also, the aging problems of transistor. Transistor age less at less DVD. Okay, this was demonstrated more than 10 years ago, an experiment in which a processor, was done by this group here, Dreslinski, around 2009. Basically, you are seeing here in their core, which is a 32-bit microprocessor. As you go down from half a VDD to, let's say, a quarter of VDD, a quarter of voltage, of course, you're decreasing the performance by a factor of 100. So it's a very steep decrease in performance here. But then, as you can see here, as the number of joules is spent per instruction is minimized, and that's the blue curve here, when you are operating around 350 millivolts at room temperature. So there are two problems that really, let's say, have to be taken into account when you are talking about, near threshold when coming to this very low VDD range. First, the timing variability increases dramatically also, and that is shown here in this curve to your right here. In this curve, you can see that the normalized standard deviation of the timing divided by the average. If you're operating here in nominal voltage, let's say you're operating here somewhere over here, okay, you have some variability that you can compensate for with this timing slack. But as you approach, let's say, in near threshold, then not only you get dismal performance, very small frequency, but you get an increase in timing variability. And then you need to apply in those systems new methods for timing margins. You cannot work with worst case timing margin, as is a common practice for many years, for many decades and decades. You have to do more creative analysis. So this introduction to near threshold computing has those two takeaway points here. First, very wide voltage frequency scaling, means the scaling frequency by a factor of 100 or 1,000. That is something that needs especially methods to design. Okay, so let me say that this is called very wide. Saying that a factor of 2 to 10 is common industry practice today. And for that, you have to really optimize and do a robust design of the circuits operating this mode. And this mode of near threshold computing is only viable if you can tolerate low performance. Okay, some power modes if you have very low performance. What could that be? Things that you have a very small duty cycle, like wearables. Things that are implanted in buildings and are seldom going up, monitoring the environment. All of those things are really nice application. And our Internet of Things came as a label, as a buzzword in the industry for trying to put everything this together. So yes, there is situations in which some applications which you can't tolerate very low performance operating modes. And some of them, most of them, wearables will be sleeping, electronics will be sleeping anyway. So here is a more general autonomic view of what you need now. To get this thing really to function, you will need basically to take care of scavenging from the ambient, okay, energy from the ambient. And you need to work on your basically system for power regulator. The power regulation, so that's power management, and there will be some digital parts here, but mostly for the power management, mostly of the power manager will be controlling that. You'll have here digital part, and then you have the RF communication, and then also the sensor. Basically, the power hungry blocks will end up being, let's say, the RF part, and depending on the sensor, that will be really power hungry. So what you can do is basically bring down the microelectronic, the electronics in the microcontroller. Okay, basically this part here that is shown, this part only, is the digital one. And if you operate that in near threshold, it can really support, the power modes in which this part can operate with very low power. Okay, I'm not going to talk about the sensor. That's a whole very complex and specialized, and every sensor is different than the other. And also, I'm not talking about, I work on the transceiver design, but I'm not going to talk about low power transceiver today. Okay, just as a basic, you students out there, you know that if you are modeling the power, okay, you have the components of the dynamic power, which has these two components here, this dynamic switching and the short circuit power, and then the leakage. Why do I include here the short circuit power separately? Well, the reason to include short circuit power here is that the reason is that in low frequency and near threshold, the slew rate of digital transitions can be very slow. So you cannot neglect the power that is consumed by the fact that the inputs of the gates are transitioning very slowly. The standby or leakage, or I call it static power, is more rigorous. So this static power here can be minimized, and it is minimized by using multiple VT threshold and by evolving the transistors from planar to FinFETs and then to gate all around. So you can do optimizations at the device level, but there are many very important techniques that you can apply at the logic and also at the system and algorithm level and in the architecture implementation. So minimizing this component for IoT is critical. And you know, as you go from to deca-nanometer CMOS, from 90 nanometer down to 7 nanometer CMOS process, whatever that means, 5 nanometer, you have to take really with a grain of salt. Leakage is really becoming important. So, and then the standby mode of this autonomic system is really takes too much time. I will not talk about the devices, just saying that the next evolution here from the conventional bulk transistor to SOI fully depleted. The next guy in the block here is the gate all around, in which the slab of silicon here, which is the green part, will be totally surrounded by the gate, which is the red part. The drive for that is basically getting down the off current and enabling higher scale of integration. So if you scale down frequency, okay, if you take the three components of power, the first one is square with VDD, the second one is linear with VDD, but is linear also with the slew time of the inputs, and the static can be related to the sizing of the transistors and also to this very strongly dependent on temperature, exponentially dependent on temperature. So the static power that you're talking about here is strongly temperature dependent, okay, in device architecture, device process, okay. Basically, today, if you look at about the scaling of the bulk transistor became impossible below 20 nanometers. So that's when you below 22, 25 nanometer, you went to FinFETs, and in a slab of silicon, the part that's the channel here, if you get close to 5 nanometer, you get to very, all the transport of electrons from source to drain is really in non-equilibrium. It's totally high field, and also the variability is humongous here because you have to have atomic precise openings. That's not practical. So yes, even if you talk about 5 nanometer technology being developed by Foundry X and Y, be aware that the source and drain are not distant one from each other at 5 nanometer only. The gate pitch is about half pitch is something of the order of 20 nanometer, even 7 nanometer technology today. So yeah, the MOSFET is not planar in this decade anymore for the state of the art. But IoT, if you just take the international roadmap of device and systems put out by IEEE or the last ITRS, if you look at the high performance VDD, the projection for 15 years, for a span of 15 years, I just want to call attention for this data here is around 0.6 to 0.9 volts. Okay, so threshold voltage is not scaling from one generation to the other, okay? And you have to take very much care. I ask you to take very much care. It's very educational information here. Don't say that a 5 nanometer technology of today is 5 nanometer in physical length. It's not, okay? But the VDD is for high performance, cannot be scaled. So let's talk a little bit about the electrical limits of nano-CMOS in terms of power and noise. Okay, if you take a system with let's say 10 billion gates that's using 5 watts of power in its most high performance operating mode, okay, we are talking that very sizable amount of power being dissipated per gate. Okay, if you had all of those gates active, you would need like 500 picowatts per basic gate, and that's really not easily achievable. And that means that most of those gates are not switching at all. Okay, and today, almost in SoCs today, most of those transistor gates here are very, very low activity. They are in cache memories that are accessed, rows that are accessed once, very, very infrequent, not at this maximum frequency. So there are lots of memory and also parts that are disabled. Okay, if you take a thermal design, envelope of 100 watts with 300 million gates, you're talking about 300 nanowatts per gate being dissipated, and we have to go about 1,000 factor of 1,000. So researching logic device needs a 10,000x improvement in power per gate if you really want to envision very active gates all the time. So if you look at the current non-CMOS devices being investigated, all the magnetic flux devices like those of junction devices that are non-CMOS, they operate in very different principle. Their supply voltage in the order of 20 to 30 millivolts only, and that really brings down the power per logic function about a factor of 1,000. But then there's always all problems of manufacturing those flux devices, those superconducting devices, and then of course they have to operate below 4K. It's a practical problem. You cannot do that for IoT devices. Okay. So the takeaway from this message here, this very brief review of power issues, is that okay, constant voltage CMOS scaling, as you can see, from duration to duration, the VDD supply is not being scaled. Cannot be scaled because VDD doesn't not scale from one generation to another. Threshold voltage doesn't scale, so you have to do constant voltage. Constant voltage scaling will not deliver nanowatt level performance, even less sub-nanowatt. Because if you take any technology, advanced technology today, the off transistor current is measured at the highest temperature corner on the order of tens of nanowatt, of nanoampere, nanoampere per micron. So yeah, you can make transistors very small, and their off current does not scale. Actually, it gets worse from generation to generation, and companies invest lots and lots to develop, process tricks for new devices. So now you're going to focus on autonomic systems then for near threshold. That's the niche where you can find, let's say, application for near threshold. But trading off performance to for power. And it's possible then to explore a very wide voltage frequency scale for the digital part and using near VT operation. Okay. But remember, a good important message is that you have to remember, for autonomic computing, highest energy efficiency is the key. Way much more important than being able to operate at the lowest power possible. You can reduce VDD and bring power down, but as I'm going to show next, it comes to a point where for digital circuits, it doesn't make any sense to go for even lower power. You have to concentrate on this, getting the highest energy efficiency for autonomic systems. Okay, and another point is that today in system on chip you already cope with dark silicon. You turn off most of the modules. Okay, or either reduce to zero the frequency or VDD. You say no operation, so that's why dark silicon. That's the only way to have no static current. Also, another technique is to resort to parallelism. So lots of domain-specific accelerators are being used in system on chip and accelerator-rich architectures. And there are domain-specific architectures that are being developed today. The hottest topics in the corner are machine learning accelerators and processor near memory or in memory which are also domain specific, that are being used to change, the design of the digital system to take care of this necessity of higher energy efficiency for those key applications like data streaming, machine learning accelerators, processing video, and so on and so forth. Okay, if you look back at the literature, the very old days of CMOS in the late 60s, okay, if you take a very simple look of a simple logic in CMOS, and you make an assumption of symmetric thresholds and a certain subthreshold slope, ideal 60 millivolt, you can get that the switching, okay, in this gate, this basic inverter, theoretically can still occur at basically 2 times logarithm of 2 of the thermal voltage. So, but remember, this is a very much theoretical evaluation. You can go and operate digital logic below 32 millivolts of supply. Okay, I can refer some papers here, but you have to use very large, very bulky inductors to be able to operate. So if you don't use inductors, pretty much you are stuck with about 30 millivolts for noise limits, and we are about 20x above this limit today with scaling the roadmap for the next years, right? But there is one problem that is basically the latch, the SRAM latch logic. I'll talk a little bit about that in the next in my talk. They really write margins just basically vanish around VDD, around 2.5 VT of the transistor. Okay? So basically, those large caches with tens, hundreds of millions of inverters, static caches, basically a good fraction of those really fail at those voltage here, like 0.6. So it's unavoidable that the caches has a different situation. And basically, you can operate logic, CMOS logic below 100 millivolts, no problem. If you can tolerate it being slow, you have a very good minimum energy per compute if you are at near threshold. But the problem is that you have to cope with these two issues here. Okay, high variability of all key performance indicators of your digital system. Okay, what is variability? But you take just a static, this is the output voltage versus input voltage in this axis here for a 9 nanometer at room temperature. If you just take, let's say, at the very low temperature here, there is a huge variability between fast N and slow P, which is this curve here for the switching, static switching, and it's low N and fast P. So there's this variability here from gate to gate. Is really the problem for scaling, and this is known for very, very many decades. Okay, so there is no problem making this inverter to work as an inverter as long as it has some gain, DC gain here at 100 millivolts. But if you don't proper size properly, it will not operate here. But my point of my talk today is that somewhere around above 0.2 volts is where the optimum energy is for most of the digital simple logic. Okay, so that's going to be the message. You don't have to go way down subthreshold logic. Okay. So I'm going to describe some experiments that we did here. We developed optimized libraries for near threshold operation in 65, 40, and 28 nanometer, all in book. Why book? Because I believe the IoT has to be cheap, and most likely, if you can do away and use book technology, which is maturing cheaper, will be used for IoT. But we characterize it with electric library, characterize it directly the rise and fall transition to tune the widths to maximize the static, static margin. And of course, you can have any driving strength as long as you keep balancing the rise and fall transistor. And basically, this is easy to do, and we do like an example of here, very simple for first year logic design students. Here have an inverter, and this NAND, and so on and so forth. The question is, what is for a given technology? You have to find the optimum alpha, the ratio between M3, M4, and M5, and M6. So I call this basically the alpha ratio here, where K is actually the strength of cells. So we can build the strength basically increasing this. And also the optimal ratio, inverter ratio here has to be determined. So for a single inverter. So if you take those cells that I have here, basically those 4 transistors here in the AOI22, they are sized by this factor, and we explore what are the optimum factors for alpha P and alpha N for sizing this cell. You notice here that I don't have fan-in larger than 2. Excuse me, or fan-in more than 4 inputs, but with restriction that there are not more than 2 transistors in series in either in this pull down on the collapse stack. The reason for that is very simple, okay? Is that the timing variability that I spoke about minutes ago increases way much, basically, when you get skew in the fast N and slow P, or with low P and fast N. The corners, the timing corners, really change a lot. The variability change a lot if you put more transistor on a stack. Okay, and our goal here is to scale down the VDD, and then you have basically developed a library in which we do not have a stack factor larger than 2. And this alpha is a stack factor in the sense that you have to make basically M2, M12, and M13 wider than M11, and the ratio of those transistors here also has to be sized up. So we do the exploration. Basically, the asymmetric corners have to be characterized. And if you go to deep, let's say, sub-nanometer scaling, one other reason why you don't want to use cells with too many inputs is that for deep sub-3 nanometer, especially FinFET, layout regularity is key, because they are using multiple patterning for doing the FinFET, double patterning, triple patterning, even quadruple patterning. And also you have this problem. And another reason to have a very small number of inputs is that metal scaling, okay, is much more difficult and slower than gate scaling. So all those reasons, okay, plus this problem of variability at low VDD, makes it a very good point, a very good case for you to use simpler libraries with less stack transistor, and this issues that has to do with basically routing and regularity, and basically calls for library cells that have not more than 2 stack transistors. Okay, and that's what we did. Basically, we take every cell that we are optimizing, we put a ring oscillator here, and you can optimize that for energy per logic event, for area, or for performance, or maximizing the frequency. So every cell, I just put here this simple inverter cell, can be optimized according to a cost function that could be, let's say, a combination of a weight K1 or weight K2 in energy and maximum frequency. So you trade off by varying K1 and K2 if you want to optimize for performance, which is the blue, or energy. Also, there is another optimization here of this ratio here of the pull up to pull down in terms of area and frequency. You take here basically we took 3 cost functions: energy, frequency, area, and area, and the symmetry of the slew up and down. We presented that in the last CASS 2020. And basically, you can see that for any given technology, using this methodology, the designer can choose the library to, let's say, to be very efficient in energy and not high performance. Or you can price more symmetry and slow, transitions that are optimized. So this is the optimum ratio that for if you use a function F1, energy and performance and minimum cycle time. The minimum is somewhere over here for this technology. Okay, this is a 40 nanometer technology, but we need that for 40 and 28 nanometer. So you have a large number of range here of inverters that are acceptable. But if you look at the minimum here for, let's say, when you trade off area and performance, the minimum is somewhere over here. But you're not much insensitive, okay, to choosing here the ratio. You do that for the sub-threshold. The optimum points turn out to be a little bit, the optimal ratios are different than the nominal voltage. So we did that for the near threshold and also for 900 millivolts. Those transistors here have a threshold about 340 and 80 millivolts. So why we did at 300 millivolts is optimization, because there is lots of evidence, okay, that CMOS, FinFET or book, both technologies, they have around a minimum energy point for maximum energy efficient is around 300 millivolts, as we're going to show. And here just show that if you take this area and performance metric here, at sub-threshold, the optimum is different than on the nominal. So all libraries are provided by the foundries for the nominal VDD, not for the low VDD. That's a takeaway point that you have to take into account. Okay. And basically, when you look at the best WP over WN ratio, basically you have to take care when you use cells with low strength. Okay. So the K factor there, the strength of the cell is low. So you have, close to minimum W transistors. You have to be careful because the optimal ratio for those cells are not the same as if you use a strength 4. Okay. And the optimal ratio, as I told you, for the 3 optimizations are slightly different here. If you're optimizing here for energy and performance, we are using here equal weight for energy and performance for this data here. But you can do any weight you want, and then you can find the optimal ratio to size your cells. The other key takeaway point is that the different strengths, like very common X8 in library cells, X6, X1, X2, and X4, those are not much used, right? But we did all of them. So the bulk cells here, okay, yeah, pretty much you can show the optimum ratio for those. And if you use basically compare that with cells, okay, the cells that we designed based on this principle for those 3 functions of optimization, 3 optimization functions, and compare with we compare with the cells from the commercial library, from a digital cell library that's provided by the foundry. And here you find in this table, it's a very busy table. I apologize for that. But anyway, at any rate, what I want to say is that we compare, let's say, the average current, we compare the energy, average energy, the energy delay product for all those three strengths. So let's take a strength of 2 here, just for comparison. Okay. If you use this let's say metric of energy, we reduce for extent of 2 reduce the energy per transition for all those cells here with respect to the commercial library. We reduce by a factor of 1.7 or 2 point or factor of 2, or reduce by a factor of 1.2. So we all that's green here means that our methodology for sizing the library, optimize it for near threshold, is at the gate level itself. It's more energy savvy in every case. Okay. Now we can lose and we increase, for instance, for demand here. We increment here in this area of the average, let's say, delay. So delay average. So in this case here, yes, we have 1.7 for all the 3 optimization functions. We have 1.7 is lower than the commercial library, but we are more energy efficiency. But we are already talking about very small performance, very low performance for sub-threshold operations. So having this average delay here twice as large for inverter, twice as large for a NOR, an AND. It doesn't take you a hit because basically you can compensate that with the VDD, the scaling that you do in your threshold. Okay, so the area cost comparison in this case here for all cells that we consider on strengths here, all strengths and cells, basically our area here is always smaller. That means minus means smaller, and the red here is larger. Okay, except for the NOR2 of the smallest strength, we have a smaller area than the commercial library. Okay, so this is a result here that shows how we do that in more detail. For instance, this is for the NOR cell. The NOR cell has to show this different behavior for the smaller strength here for this 40 nanometer technology here, the NOR2 smallest strength. That happened also in 65 nanometer. That basically this is very busy. Here is the ratio of rise to fall time. So the rise time normalizes to the fall time, and here is the propagation delay, and here is the alpha, the factor of compensation, increasing the W of the transistor. Okay, it makes sense. Okay, but that's basically it makes sense to use longer than minimum L for the NMOS transistors in a NOR cell. In this case, we are using like 50% longer, and because that diminishes the alpha factor here that increased the transistor size in the PMOS array, and lower alphas for equal rise and fall time save area by a factor of 4, more or less. So using minimum L in some cells for subthreshold low performance makes sense. Here is a case of optimization of the alpha P for the pull-up network here, and the alpha N for sizing by a factor of alpha over these transistors. Basically, we are optimizing those 8 transistors here, and you see that it tries for different alpha P's and for different alpha N's, and you can basically tolerate some asymmetry in the rise and fall or make it very similar. Okay, but in the end, if you make alpha N equals 0, okay, you can localize here with the smaller alpha P. Okay, so you have different trade-offs in area. If you do this, you can have saves in the area, but tolerate a larger asymmetry in rise and fall. So the same thing here for the NAND. I'm not going to go over this detail. We have much more to cover. The same optimization for master slave registers that have to work in near threshold. So we are using here basically this master slave, and we are optimizing the clock drivers, okay, that drive those switches and those 3-state inverters here. And basically you see that there's no more than 2 transistors stacked here for doing a preset. And we optimize the W of those all those gates that are in pink here. So we did that space exploration to get a register that consumes the less energy, and then you can have different sizings and all those points here, different sizes. And here you see the average energy in femtojoules for writing and reading this cell. Okay, for a D flip-flop with different strengths. So basically, you look for the Pareto curve here for the D flip-flop of strength 4. The Pareto curve is this one, and you see that you are seeing here clock to Q delays at 300 millivolts of the order of hundreds of nanoseconds, right? So this is targeting for operating at 300 millivolts, and then you can choose, okay, the design here of this flip-flop, and then we have a library of the flip-flops that we optimize it for energy in this way. So this is a cell library. It has all those strengths, X1 to X8, and those basic cells here. They use it. We use it cells with regular VT and low VT cells also. Okay, all of them were characterized with the cadence cell characterizer at 300 millivolts. Why do you characterize that at 300 millivolts? So why do we size them at 300 millivolts, but then we'll characterize them for operation at 0.2 to 1.2 nominal, 65 nanometer in this case. So the electrical library characterizer, we extract the Liberty files for increments of about 10 millivolts. So we can have the hundreds of lib files to be able to extract the data that I'm going to show you next. So we did that for 8 benchmarks, sequential and combination circuits, and 2 circuits that are of the order of 8-bit microcontroller or a notch filter with about 24,000 gates. These sequential circuits here, they have a balance of combination to register logic, which is typical of random logic. And what you see here is that I have to call your attention. This is the energy that we dissipate running some core, let's say, some core instructions and using some kernels of instructions in this core at room temperature. And at each VDD here, you go for the maximum frequency, and you see what's the energy that you dissipate to execute those thousands of instructions of those kernels. So this energy that you spent for executing those instructions at the maximum frequency that is allowed. Of course, here you are at this voltage. Here we are operating of the order here of gigahertz over gigahertz, and here you can see that the energy that is dynamic, static plus switch plus short circuit, it goes down with VDD, and the energy to execute this kernel goes up, and you find here the minimum energy point. So there is a minimum energy VDD, an optimum VDD here, at which you have the maximum energy efficient to execute code. But you in a processor, you execute code, right? So the fact is that at the near threshold point, and if you operate at the VDD of the maximum energy point, maximum energy efficiency point, you have a performance that is 10 times larger than if you, like, say, operate at 200 millivolts. My point here is that has been lots of research on subthreshold logic, subthreshold CMOS logic modeling. Okay? But this is a compelling, very simple example to say that why you want to go to ultra low power, which is allowed by 200 millivolts. If to execute any task, you consume more energy. Basically, your static energy here for the sigma windows here, the 3 sigma windows here, that's the worst case energy static, and the best case, worst and best for all those VDDs. And how we got those points here? Basically, we got all those points by doing a library characterization of the cells that you optimize at the sizing for 300 millivolts. We did characterization of those at all those VDD. No company does that. This is an academic work. Companies most likely use a nominal voltage and minus 10%, plus 10%, and sometimes one low power mode here is some voltage here, and they provide you 2 or 4 dot leaps for the same line. So the question is here that basically you're taking a hit here from performance going to sub megahertz for the optimal. Okay, you are sub megahertz operating at 300 millivolts. But the best energy savings for this temperature. So if you can operate a megahertz or a fraction of a megahertz, you're for doing housekeeping and standby operations, you better do it. But the point is that why you see if you look at power goes way down, monotonic, but energy gets a minimum point. That's the whole point. There's another message here, very interesting. Okay. When you operate near or just below the threshold, and you operate at the minimum energy point, the hotter the circuit is, and here's the case that the same circuit with the same cell library, the same circuit is being characterized at 125 Celsius. So at 125 Celsius, this circuit at the minimum energy point is faster. So because you're operating here in the subthreshold regime, okay, and given the fact that the threshold of transistors, CMOS transistors, they have a negative temperature coefficient, okay, so the threshold goes down as you increase the temperature, basically this effect makes the circuit run faster at the minimum energy point. Of course, the energy that you spend in this here, static, is exponentially dependent on temperature also. So if you compare this with room temperature, it's orders of magnitude higher. And basically, the minimum energy point here happens at around 320 millivolts or so, and it's way faster. It's at 2.7 megahertz, which is almost 10 times faster than at room temperature. So yeah, the hotter it is, okay, the hotter it is, the faster goes the circuit in this near threshold, which is the opposite of what you suppose from super threshold operation, which is the nominal one. Okay, so yes, you go from here dozens of megahertz only to all the way to gigahertz, and near threshold computed, there is something missing here at minimum energy points enable much larger gain in energy efficiency. If I'm not mistaken, it's about roughly about 20x gain in energy efficiency here from super threshold to low threshold. Now, if you go to low temperature here, then you kill basically kill the static leakage component, but the near threshold minimum energy point has performance is still 5 times larger than if you operate at 250 millivolts. Now, if you go at 200 millivolts, it doesn't even operate because the threshold voltage goes up as you go down to temperature. Okay, I'm not going to tell much more about that, but just we did that for the notch filter. The notch filter has many more registers, and the minimum energy point is about 320 millivolts for this architecture. You get 15x higher performance at this near VT, okay, than if you operate in sub VT, way sub VT. Of course, here now you're 100 kilohertz only for this maximum energy efficiency. Okay. If you go to higher temperature, you have more registers. The minimum energy point goes to the right. Okay. The performance also increases the temperature, and also if you look at the super threshold performance here, the performance at super threshold goes down because here you have the temperature reduces the mobility of the carriers of the channel, while here you are operating mostly in the diffusion mode of carrier, and in diffusion mode, basically you get more diffusion current at higher temperature with the lower threshold that you have. So those are the key points for this. Hotter is the better, okay? And if you did that in the lowest temperature corner, the minimum energy point is even larger, but the difference in frequency here is not large. And we did that for all those cases, all those 8 circuits here. So I'm gonna highlight for all those designs here, we find the minimum energy point is always around 0.32 volts. Why you can state with this precision is that because remember, we did the library characterization for VDD in increments of 10 millivolts, okay? Which is not done at any company. They scale the timing in power parameters by a rule of linear interpolation. Okay, so if you go from super VT to minimum energy point, you can energy on average for all those about 100x. So this is the energy at the green at nominal voltage, and the energy that you do for the same operation here. If you operate at the minimum energy point, with the blue is here, you gain on average, of all those circuits here, 100x in energy per operation, which is good. And also, I make a case here that even though people defend, have studied sub-threshold logic, 100 millivolts, 150, okay, the sub VT at 200 millivolts, okay, the energy efficiency is worse. Okay, even though the power is less, it just takes longer, and because it takes longer to execute, it takes much more energy, static energy. So that's the reason why I'm not that fond of deep subtraction CMOS logic. It's a scientific curiosity indeed. Okay, performance varies from hundreds of kilohertz to a megahertz all the way to gigahertz. From temperature, if you go from, let's say, so the frequency scales exponentially here from the nominal VDD to the minimum energy point. The minimum energy point is the blue. So yes, you have to tolerate low performance. We did a different comparison here with 2 generations of those cells we published many years ago, but I'm not going to go. There are ways to still increment the library and make more diversity and get some better results. But we did improve that. But again, we did at 300 millivolts. The sizing optimization was done 300 millivolts. One point I'm going to describe one experiment that we did now is that you scale down VDD, you bring down also the noise margin. The static noise margin goes down, and we define in any textbook what's the noise margin low and noise margin high, and you get from the negative slope here a definition. But you have to be careful that indeed there are 2 other criteria that are used for SRAM and basically pairs of inverters, or and also all those situations here can occur in a logic path, in a timing path, a NOR driving an NOR3, an N2 then driving an N3, and all that. We consider all those 15 cases here at 250 millivolts using our library that we optimized, and look at what happened with the static noise margin if you use the negative slope criteria that you find in any textbook, and those that you are using in the memory, literature. Basically, the static noise margin can be defined here by the smallest of those 2 butterflies, and if you use the maximum area of not a rectangle but a square, or maximize the area of a rectangle in which the noise margin low is different than noise margin high. We basically did an exercise. I'm not going to describe that. We did the sizing of the cells. We operated at the near threshold. Look at with the Monte Carlo what happens. We found out that for random logic, it's better to use this criteria here. Is the one that is less pessimistic, is more realistic, and is less pessimistic than the other 2. I'm going to go fast about that. So this is the Monte Carlo. What is the static noise margin at 250 millivolts? We're talking about 50, 60, 80 millivolts of static noise margin. I'm not going to go to this detail, just saying that basically when you look at the variability of static noise margin, compare with other methods for sizing, we sized our libraries for with a method in which we improved this sigma over average of the over several works in the literature here. Some that using the symmetric channel length, other uses other methods. About 50 to 60% improvement with our methodology for assessing the static noise margin. So the takeaway for this experiment that I'm not going to describe in detail is that Monte Carlo analysis at near thresholds, basically you have to do S&M switching only the input closest to the output rail when you do the static noise margin, do that. And also use the maximum square in the butterfly, the smallest butterfly, because it predicts better the average behavior static noise margin under process variations, which are 2 important in subtraction. Okay. So and also using non-minimum L and minimum strength requires careful consideration of the cells when you size them for near VT. It's a word of caution. I already mentioned that prior when there is small strength cells sizing. So these are recommendations for those people using design and near threshold logic. Okay, the last part of the talk is based on idea that Crovetti from Politecnico di Torino published many years ago. It's basically what he proposes using analogs instead of using conventional analog CMOS, for signal amplification, use digital logic. Okay, So you know, the operation transconductance amplifier is the bread and butter, is the basic building block for analog. Okay, in normal voltage or low voltage. Okay, what is being proposed here, okay, and we did is basically, instead of using the conventional op-amp, okay, differential transconductance amplifier, could you also design this way of amplifying the difference between those two signals, the input here and the negative input here, which is a feedback in the feedback? Can you replace this blue block here just by digital gates? Okay, and using just two input logic that can be able to, we'll be able to use it at very low voltage. That was the question. Okay, and we have basically the idea here is, the key concept is this. Okay, the message is the following. Okay, you want to amplify the difference between those two signals and put this thing out. So is there a way to develop that core totally digital? Here's the challenge. Okay, and here, can we do this conventional OTA using just gates? All this here gates, and this is the digital buffer. Can we do it? Okay. Basically, what you do, you use here basically a switch that you basically can turn it on or turn it on to charge the capacitor, a switch down to turn off the capacitor, to discharge a little bit the capacitor, and do that in a way that it reflects the difference that you get here between those two signals. So what you'd like to do is basically have the following. So you want to amplify here VN prime plus as a proportional to 2 voltage, one that comes from the common mode. What is the problem? What's the main problem with the buffer or any inverter logic or digital buffer? Is that the switch logic threshold varies a lot with process. I already mentioned that in the beginning of the talk. So varies much. So you have to compensate this common mode that you have here, and using a summing network here that somehow will sum or subtract a certain amount of voltage to this node or to this node. Because what you want ideally is to have an analog amplification, is that you want to have in this capacitor voltage here to reflect some gain factor over the difference between those two. Okay, and the problem with using the inverter as an amplifier is that the optimum the switch point of them of the inverter varies with process. So here is the solution, and there is this year a paper that came out in 2020 that shows that the fabrication results, the measured results of the digital-based analog processing at very low voltage. The principle of operation is this. Okay, you have to use here. Okay, simple. That's the only analog component here are those transistor here pair. This transistor pair, which reminds you an inverter that's connected in this strange way, and in sub-threshold, so that this is a large resistor. So you have two resistors here to sum the common mode voltage in this node of this input. Okay, and in this both this input. This is the VN plus and this is VN minus. Okay, so this logic gate, this buffer here is basically 4 inverters in series. Okay, and this is a digital logic. And now you have to do the following. You have to come up with a logic function here, which is very simple. Okay, which will compensate when this point here, X out plus and X out minus, are both high. That means the common voltage is way above. So they are above the threshold logic of the inverter. Threshold logic of the inverter is somewhere over here. So both VN plus and VN minus are both. So what you have to do, well, you have to subtract voltage from these two nodes. Okay, and if you are let's say, let me show here, if XL plus and X minus and plus X out are both below the threshold of logic, you have basically to increase. Okay, So what you do here is you come up with a logic. What you like to put here in this node, compensation node here, to increase or decrease the common mode that is in those two inputs here. And this logic for driving the output stage is shown here. Okay, and here is the logic for the common mode voltage extractor. If simple the logic you see here, you come up with just those inverter in north for this logic here, and for this logic down here is just those two gates. Very simple. And the conceptual is this, you know, if you common mode voltage is above the threshold of the logic, if it is below, if it is the differential voltage is positive or is negative, and then you would like to operate here in order to make this amplification. You can, let's say, drive very large loads, okay, with very low supply, and that was shown by Pedro Toledo, who is now doing his PhD in Europe. He did basically the digital logic here, which is this is the only analog part here. The common mode extractor, basically in the output stage are two transistors. The buffers are digital here. All those digital logic here was implemented in 180, 130, 40, and 28 nanometer, and here it's published this year the 180 nanometer results, and we have others coming up very soon. So what happens is that you are in the output. You are able to follow. You are able to follow the output according to the difference between the inputs. And here you see the input, changing. This is an example in which you are doing using this digital based operation transductor amplifier. Configure in the unit gain mode. It's very easy to do that, unit gain. So this V in should be tracked by V out, and this is the input response. Let's say the output response to respect of variation on the input. Okay, so you are using the digital OTA here as a follower, right? Basically, as an impedance, impedance matching from high impedance to low impedance. And basically, you see here the digital logic that amplifies is only consumed 35% of the power, and the output stage consumes about 55%, but this is on the order of nanowatt because you are driving a very large capacitance here, and you are consuming just 2 nanowatts doing following this voltage. You can see that the bandwidth, okay, that's the key takeaway point. At 300 millivolts of supply, okay, for all those gates here, at 300 millivolts here, the bandwidth that it can sustain is really, really small. Okay, you're talking about kilohertz bandwidth here for this amplifier, but you are dissipating of the order of 2 nanowatts. And here, I think it comes experimental result. No, that's still simulation, but that's experimental result. Here is the gain that you can get, the DC gain of the order of 30 dB or a little bit larger, according to the capacitor that you are driving from 10 puff to 80 puff. And here you see the bandwidth, the gain bandwidth product of this is of the order hundreds of hertz or kilohertz. And if you take the figure of merit of energy efficiency of this, okay, the energy also is, if you use this amplifier at 500 millivolts, 400, 350, 300 millivolts, it is an analog amplification function. And if you look at figure of merit of energy, the best, let's say, the best optimization of energy that is defined here in this reference 15 is at 300 millivolts. And the figure of merit that trades off energy and bandwidth, it also peaks at around 300 millivolts. So it's a totally different analog function, but we are using just gates, and the only components here that which are not gates is this very strange connected, this connection here. Okay, so I have to change the color here. This connection here is inverter connected this way. That emulates a very high resistor, and those the driver stage here that resembles an inverter, but it is driven by two to signals like a charge, you know, as you find in a PLL. Okay, so basically, you know, this analog function is also found on optimal around 300 millivolts. And of course, if you can bring down the voltage, as I told you, you can always bring down the power to sub-nanowatt level. But the optimal energy for obtaining this source and this OTA is around it. We compared against several other op-amps published in the literature with mature technology nodes, and our basically our figure of merit for speed and power, you know, it's better than everyone else. This is the figure of merit S. That's the bandwidth times the discharge here, which is CL divided by I, the static current. Okay, the figure of merit takes into account power and bandwidth. So our digital OTA here with Monte Carlo, the variability here falls in this region here. It's the highest figure of merit for slew rate, normalized by IDDCL and bandwidth. So it's better than most of the analog here at the very low frequency. Okay. Anyway, it's about the time to wrap up the message of this talk. First, our floor is IoT. In IoT is very important, but energy floor is the one that's essential for IoT. So the digital part of the IoT system on chip will benefit from very wide voltage frequency scaling. That was another message of this talk. Near threshold CMOS is energy efficient as no other one, but it's low. And it was being proven by this work on analog digital OTA to substitute for analog OTAs, operation transconduction amplifier. That okay, near threshold logic is also very efficient for very low bandwidth, let's say instrumentation level type of things, which is useful for many sensors in IoT. And we develop also a cell library maximizing energy efficiency and robustness for meaningful improvement in delay and optimizing for energy. So that's wrap up my talk. I have to acknowledge here the collaboration that we had with four master students who worked in our group here in the analog mixed signal group in Porto Alegre. Pedro, who is now in Polytech Torino, Kleber, who is now in Waterloo, Rosa, who teaches in the Federal Institute, and Felipe, who is working in Porto Alegre for Silvaco, and my student Rodrigo, undergraduate in computer engineering, and my colleagues and collaborators in the digital OTA, Professor Covetti in Torino, and Hamilton here in CG Micro in UFRGS. And Covetti also was the first to propose using these digital gates. And we came up with optimization to make it the energy efficiency even better with this principle that we just spoke today. And there is already a mini tutorial next Sunday in ISCAS given by Professor Covetti, in which not only the digital OTA will be presented, but also a digital analog converter using mostly digital gates only, and also other modules. You know, will be presented in his talk in the tutorial this Sunday at ISCAS. Okay. With that, I conclude. I'm open for questions. Thank you very much. Here are some references for the work that was in the table for comparison. Sorry for the going over time, my dear friends of the Grande chapter.
Okay, thank you, Professor Sergio Bampi, for the nice talk. We have actually one question from Luis Eduardo Palomino Bolivar. The question is in Portuguese, but I'll try to translate it. So he's talking about harvesting. So the harvesting can polarize the integrated circuit with a voltage of almost close to zero threshold voltage, right? To start the capturing of electrical energy. How do you comment about this technology?
Yeah, I did not talk much about harvesting, except that is needed for the autonomic computing. And those near threshold circuits, digital and the analog functions, are very suitable and very good candidates to be used in systems in which the energy is provided by harvester. The question that Palomino made is that the system, okay, the harvesting can bias the near the threshold. Yes, okay, and also the startup. I think Eduardo Palomino Bolivar, who is in Santa Catarina, by the way, he teaches there. Eduardo, indeed, this startup for the harvesting needs zero threshold transistor, as you mentioned, but you are talking about a different subject, which is basically getting a very small amplitude, let's say, source of energy, and doing an AC to DC, a rectifier, which does a step up. Yes, indeed, using VT zero transistor with zero VT is important, but for the digital functions that I mentioned, the library, the cell library that I developed here at UFRGS with my master students that I referred today in this talk, we use it only regular VT transistor, not zero VT, and not even low VT. The low VT poses problems here in terms of leakage. So you use low VT when you need high performance. So we are operating near VT. We are operating in low performance. Means that using zero VT transistor is important for the AC to DC conversion that we referred. Okay, but for the digital logic, don't use the zero VT and the low VT to operate at near threshold 300 millivolts or so. That's my point. So he made a follow-up question. What is the consideration with respect to this zero VT technology for IoT? Yes, for the energy harvested, Luis Eduardo, yes, indeed. The zero VT transistor is very handy. And if you look at, we are working here at some designs of 28 nanometer book. The PDK that we get from the foundry doesn't have a zero VT transistor, but we do have the zero VT transistor for 108 nanometer technology. Okay, so some mature technologies have a better variety for optimizing for IoT.
Okay.
I hope to have an answer to Luis Eduardo Palomino.
Yeah, sure. I have a question. It's a general question. How do you think about this library that you developed in your group? What's the steps now to turn into a commercial library?
Well, we have not put that in GitHub or made it available because basically we did a library for 65 nanometer commercial technology, commercial PDK from ST, and I don't have a legal information if that would be viable, let's say acceptable for us to put a library in the web, which is based on their technology, their PDK. There are lots of restrictions when they license that for university academic use. I have to call your attention because the data that I showed today to try to find for every circuit the minimum energy point. What is the VDD that provides the optimal energy efficiency? We did that because we used a commercial tool, okay, to characterize with a commercial PDK a cell library that we sized it. We developed here in our group with the master students that I mentioned with you. And then that library, we characterize it at 10 millivolts VDD step for all power and timing and slew rates, transition times. So yes, it's a lots of work, okay, characterizing them, and that's the only way that we could find the MEP. And the most interesting data, I didn't share this data with you, but in 2012, when 20 nanometer book FinFET technology from Intel came out to the market, and the public announcement, they also published a paper in the ISSC conference in that year, 2012, which show a unit of one of their core processor shuffle unit, some of the SIMD units that they characterized separately to find the optimal energy point for that 22 nanometer CMOS FinFET. Well, the optimum energy point for room temperature of data is about 290 millivolts. So if it is CMOS book or FinFET, the minimum energy point is around that value because it has to do with the threshold of the transistor, which is not changing much from technology to technology, and it has to do with the temperature that you are operating on, and it has to do with also with the third factor is architecture dependent. It's amount of random logic combination and the amount of memory registers, and that optimum does not take into account, okay, caches, because caches will get really bad performance and lots of error if you reduce VDD as aggressively. So you have to use different power domains for your block SRAMs and your logic with register and random logic. Okay, so indeed, it's very important that you know if you work in CMOS, this energy efficiency has to do with the basic characteristics and of the devices. Okay, and has impact and suffer impacts from the temperature and the architectural features that you have.
Okay. I think we don't have more questions here, so I'd like to thank again Professor Sergio Bampi for this excellent talk. And
I thank you from the Rio Grande do Sul chapter of CASS. I know Claudio, José Rodrigo, Ricardo Reis are board of the chapter, and I congratulate for the series. I hope to have contributed. My group is working in several different areas. We are working on near approximate computing for accelerating neural networks, video, and we have other areas. We have a group with Professor Hamilton who works in reference ultra low power, sub-nanowatt voltage references, and we also have a subgroup working RF circuits for transceivers in which you are pushing the boundary. For instance, we just published today, a thesis by Mateus in our group, Mateus Moreira, in which we are showing an oscillator that is working at 300 millivolts, also 320 millivolts, consuming for almost 2 gigahertz oscillator, consuming on the order of 100 and 150 microwatts at the worst corner. Okay, so yeah, so we are also working in gigahertz circuits at low VDD, which are very challenging. There you need inductors to make this. Thank you.